Okay, so we are going to understand entropy, the concept of entropy by taking microscopic point of view. Here is a diagram. Here is a space which is divided into 4 parts. Okay, so one could imagine later on we can say that these 4 objects can be treated as 4 molecules because we will be dealing with gases. But the principle remains same. So what we have done is, let's say this is our system. That means I'm showing a dotted line. Let me use another color. So this is our system. In this system, the 4 objects are placed in 4 spaces. These spaces are formed because of the 2 partitions. Okay. So now this particular arrangement, meaning that the red object is on the left hand side uppermost corner, the blue object on the right hand side uppermost corner, etc. This particular arrangement can be called as one microstate of this system, right? This is total system. Of this system, this is one microstate. Now if I change this, if I take red side here and blue side here, blue object here, so now this becomes another microstate, right? Now green object can come here, red can come here, that will be yet another microstate. So this is a single system can have many microstates. So now we can say that entropy is one for a system, the system which can have more microstates can be considered as a system of higher entropy. Higher the microstates possible, higher the possibility of microstates, higher is the entropy of the system. Okay. Now suppose if I increase the space, that means there are few more space or positions possible. Let's say we extend this box and there are 2 more positions possible. That means now these objects can occupy these spaces also. So number of combinations will be increased. Possible combinations will be increased because of increased freedom for these objects. So number of combinations will increase. That means number of possible microstates will increase. Which means now this system has to be extended. This system, which is marked by the system boundary, now has increased entropy. Its entropy has increased. Similarly, so when we increase the space, so if I can add one more square, the entropy will be further increased because number of possible microstates are increasing. Similarly, if I increase the objects right here, if I say there are one more object, add one more object, now the possible microstates will further increase. You can imagine that. It's not just because their combinations can be many now, because more than earlier, because not just space has increased, number of objects also has increased. So entropy has further increased. Okay. So this is the concept of entropy. Number of possible microstates. If that number is increasing, then the entropy of the system is increasing. Remember that a particular microstate doesn't tell you that whether the entropy, it doesn't tell you about the entropy. Possible combinations, if there are more and more combinations, that means more and more microstates of a system, more is the entropy. Possible microstates, more is the entropy. Now in the previous video I had given you one analogy. I said that in common language, our understanding of order and disorder is highly subjective. If we consider 2 rooms, one bigger of them, in that bigger room, if there are few objects, table, chair, books, rack, etc., rack for books, few objects, but everything is placed where it is. The chair is placed just in front of table, the flower pot is placed right where it should be placed, books are neatly arranged, right? Now this is one room. Second one, which is smaller than the previous one, it has many objects and the objects are not placed where they should have been placed. maybe there is a table on which chair is placed, right? And the flower pot is placed on that chair, or the books are placed on the table instead of on the rack. They are scattered on the table. Okay. Now if you look at these two rooms, you will be tempted to say that the first room is an ordered room, but that is your subjective thing. Objectively speaking, if you want to apply this logic which we have understood here to these rooms, then you would say that it doesn't matter whether the books are placed in the rack and where they are placed. It doesn't matter. The point is how many possible combinations are here. If this room is bigger, and in this room there are many, you can have many combinations possible, then this room in fact will be a disordered room. In fact, I should have said that there are many objects here, and all the objects are placed where they should have been placed. Okay, let's imagine this room, a bigger room, has many objects, and all of them are placed where they should be placed. Should be placed in the sense our convention dictates where they should be placed. Okay, so everything, books neatly arranged, etc. But this room, by this definition, is more disordered because there are more combinations possible. You have a lot of freedom to place the objects anywhere in which you like. But if it's a smaller room, and now I'll correct this, and small number of objects are also smaller here, then by this logic, this will be more ordered room, in spite of the books being placed on the chair being placed on the table, etc. Right? So this is the point. Our idea of order and disorder has subjectivity in it, but we are talking about science. The objective criterion of science is number of possible microstates. Now let me add a few more things. Now just think about this gaseous system and consider them as molecules. Okay. Now say this system, if you supply heat to this system, what will happen? What will happen to the disorder? Now you can logically say that when you heat something, the randomness, because the heat is associated with randomness of molecules, right? Heat is energy associated with that. So if you are heating a gas, then the molecules will be, gaseous molecules will be excited, and randomness in the system will increase. That means what? That means there are now more microstates are possible, because molecules are excited, they are moving here and there. So which means there are many more microstates possible. So logically you can say, or not logically, I should have said intuitively, you can say, when you heat any object, right, then the disorder or entropy of that object or system, gaseous, anything, solid, liquid, gas, and if you can consider that as system, entropy of that system should increase. Because look at microscopic level. What will happen to the movement of molecules? Randomness will increase. That means more freedom. In fact, it's more freedom for molecules. More the freedom for molecules to move, more is the entropy, more is the disorder. By the same logic, if you take out heat from any object, then the entropy of that object or that system should decrease. By the same logic, just reverse the logic. You are taking out energy, so obviously the molecular random movement of molecules will decrease, so entropy will decrease. Now this is the concept of entropy, which we have understood by taking microscopic point of view. Remember, this discussion you will not find in any book which strictly adheres to classical thermodynamic norms, because we are not supposed to get at microscopic level and understand it. We are going to deal with only macroscopic. So in this case, if it's a gaseous system, the macroscopic properties are only pressure, volume, temperature, which you can sense. But if you want to really understand the physical meaning, we should get at microscopic level and try to understand the physical meaning of entropy. Now the next question is, how, if you are not going to take microscopic point of view, and if you are going to strictly adhere to macroscopic point of view, which is classical thermodynamics, how do we encounter entropy? Because we cannot talk about order, disorder, then how can we understand entropy? How do we come across entropy when we have a macroscopic point of view? Because just think, if there is a gas and if you want to measure temperature, you insert thermometer and you measure the temperature. The molecules, at molecular level, many things are happening. Molecules are bombarding against the thermometer bulb. But the effect of that is what matters, and that is macroscopic property. We don't look at molecules, but the effect of that can be sensed by us, can be seen the thermometer bulb rising, you can see that. So the macroscopic property is what we can understand. Okay. Similar thing is about pressure. So pressure, temperature, volume, these are all macroscopic properties. You can measure them. It's not possible to measure the entropy. There is no instrument which you can insert in the object or in the gas and measure entropy. It's not possible, right? So if that is the case, then how we encounter this entropy, right? This entity entropy when we are discussing the things at macroscopic level or in classical thermodynamics. This is very interesting, and that's what we will do in the next video. Thank you.